It's been a while since we've done one of these. Welcome back. Starting a new chapter. A very fun chapter, I think, but it can be complex, so you are going to want to read the book. I would recommend for this first section that you at least take a look at pages 175 to 188, as well as some pages from the next chapter, pages 227 to 229, because this unit is actually going to be a combination of a chapter on bonding and a chapter on naming compounds. First, we're going to start with covalent compounds. So first of all, really the question is, why bonds? We've talked a little bit about elements bonding to each other, forming compounds. Why would they want to do this? And if you recall, we've talked about that everyone wants to be happy. All these atoms just want to be happy. So in a covalent compound, this is going to be achieved by elements sharing electrons. Covalent bonds are only going to form between nonmetals. We're going to throw hydrogen into this category here. It behaves basically like a nonmetal, even though it is on some forms of the periodic table put in group 1 because it only has one valence electron. But these are going to be between nonmetals, no metals here. So that's going to make them nice and simple. There's only a handful of things that these can happen between, because remember, the noble gases won't form any bonds at all. They're already happy. Covalent bonds will result in a molecule. So if you hear someone talking about a molecule, it's just nonmetals bonded together by covalent bonds. Now, although they're sharing the electrons, sometimes the electrons are not shared equally. See if you can remember this word from this previous chapter. That's right, it's electronegativity. I just realized what I said didn't make a lot of sense. But what I was trying to say was, even though sometimes things are shared, let's say in water, where you have oxygen and two hydrogens bonded together, the oxygen wants the electrons more than the hydrogens does because of electronegativity. It's going to drag them towards its sides of the bond. That's going to result in more negative charge on the oxygen side, and therefore a more positive charge on the hydrogen side. That's called a polar covalent bond. Polar like North Pole, South Pole. And why do we care about bonds? Well, we care about bonds because they form compounds, and when we start talking about chemical reactions are going to break and or form bonds. And there's a certain amount of energy associated with these bonds that can either be released or will be needed in this chemical reaction. That's going to be very important later this year. So, when we're doing these covalent bonds, we are going to talk some about Lewis structures. We've done some simple Lewis structures involving just one atom, but now we're going to do some larger ones. So go ahead and review your earlier notes, then come back to the video. Okay, so now we're going to be using the Lewis structures to show how electrons are shared between atoms. So, we'll do a couple of these together, and we'll do a lot more in class next time. But step 1, you're going to write both symbols. You're going to add up all the valence electrons involved. You're going to draw a bond between the atoms. A bond is going to be at least 2 shared electrons. We'll start off with at least one bond at first. You can have more. And then you're going to draw in the rest of the electrons so that all the other atoms are happy. And how many do they need to be happy? For most, that's going to be 8. Do recall that hydrogen only needs 2 to be happy. Boron and beryllium actually can do with less than 8. And some like phosphorus and sulfur can use more than 8. But for now, let's just stick with 8 and 2, just to keep simple. So, let's try something fairly simple at first. Let's try water. So, here we have an O and an H and an H all set up and ready to go. We have each of the atoms drawn in. Let's go ahead and count real quick. How many valence electrons does a hydrogen have? That's right, it has 1. So we've got 1 here, 1 here. That's a total of 2 electrons we have to work with. How many valence electrons does oxygen have? 6, that's right. So 2, and 6, we need a total of 8 electrons spread between these 3 atoms, and they all need to be happy. Well, first of all, let's make some bonds. We're going to have a bond here. That's 2 electrons shared between the hydrogen and the oxygen. And here, that's another 2 electrons shared between the hydrogen and the oxygen on this side. Now look what's happened since these electrons are shared. This hydrogen already has 2. It's happy. This hydrogen already has 2. It's happy. So we're done with the hydrogens. But how many total electrons did we need to distribute around? 8. We've only got 4 out right now. Where are the other 4 going to have to go? Well, they're going to have to go on the oxygen because the oxygen right now only has 2 and 4. It needs 8 to be happy. So we'll do 1, 2, 3, 4. And we're done. We're done with water. This is one way to represent the Lewis structure of water. Another way that we could represent these bonds here, if you have a bond, you don't have to draw both electrons. You can actually draw a line like this. Of course, your line will look a little bit better, but that line means 2 shared electrons. Let's take a look at another one. Let's take a look at methane. Don't worry about the names right now. We'll talk about the names later. But methane is going to have a carbon and 4 hydrogens. Again, we'll talk about how to name them later. Right now, I'll just tell you that this is methane. Okay, carbon and 4 hydrogens. Now let's see here. How many total electrons are we going to have to work with? Right, 8, because we've got 1, 2, 3, 4 from each of the hydrogens and 4 valence electrons on the carbon. So, let's see. Let's start with a bond between each one. 1, 2, 3, 4, 5, 6, 7, 8. So now, let's see, is everyone happy? 2 here, 2 here, 2 here, 2 here. So the hydrogens are all happy. And 8 around the carbon. Everyone is happy. Again, now that you've seen it that way, another way that we can represent this is simply by drawing these lines. These lines are going to mean a shared pair of electrons. And that's methane. Back to the notes. You can practice a lot more of these from the book. We'll also practice a lot more in class. I just want you to get these down in your notes for now. You can also have multiple bonds. Atoms can share more than one pair of electrons. Double bonds, for example. Here in oxygen, they're actually sharing 2 sets of electrons, giving a double bond. You can even have triple bonds. These nitrogens here are sharing 1, 2, 3 pairs of electrons. You can't have any higher than triple bonds because take a look at what's happening here. We have a bunch of electrons right here. Eventually you can't shove any more electrons together because they'll repel. Negatives and negatives, you know that whole thing. So you cannot have a quadruple bond. You can have single, double, or triple. Multiple bonds are, first of all, shorter than single bonds. It's going to hold the atoms closer together. 2, they're going to have more energy inside of them. Inside of them isn't the right word. They're going to represent more energy because they're holding these tighter together. And you know if you hold something tighter together, you're going to need more energy to do that. So that will be important later in the year. For right now, you can just accept these phrases. Why don't on your own you try carbon dioxide? We'll check it tomorrow in class. I don't want to make this video too long. We're already approaching 10 minutes, and I do have a little bit more I want to talk to you about. Chemical formulas. A chemical formula is a shorthand notation for a compound. For example, here this is going to tell us C8H18. It's going to tell us that there are 8 carbons and 18 hydrogens. Now, you don't read it as C8H18. You could indeed. And in fact, probably almost anyone could write this from this. But this has a name. This has a name. It's called octane. Octane. And here's a picture of it here. So we're going to be working with also in this chapter naming these things because the names are very important. Like we've called water before dihydrogen monoxide. Well, where does that name come from? Well, we're going to see that. So we're going to work just with binary molecules. Binary means two parts, just like binary in computer code means a 0 and a 1. So these are going to be nice and simple. So here's what you're going to do. If you have the formula and you want to name it, the element from the smaller group is typically listed first, so a smaller group number, like 4 before 5. If the group is the same, then the one from the larger period gets named first. You're going to use prefixes to show how many atoms there are. We'll see the prefixes on the next slide. And the second element listed, you're not going to keep its same name. For example, if it's oxygen, you're going to drop the ending and make it oxide. If it's chlorine, you're going to drop the ene and make it chloride. We'll practice with this. Just get these down in your notes first so that we'll have these 3 rules in class. Okay, numerical prefixes in. How do we use these words? Well, if you have one thing, mono, 2, di, 3, tri, 4, tetra, 5, penta, 6, hexa, 7, hepta, 8, octa, 9, nona, 10, deca. These aren't really new words. You probably know them from geometry, a lot of them. Triangle, pentagon, hexagon, octagon. Probably don't see a lot of decagons, but decade, 10 years. Mono, just one thing. Di, like a... blanking right now, but there's some things that you have diatoms in biology, I believe. Okay, so let's take a look here. Into H4. See if you can follow the 3 words and name this. Go ahead and pause for just a minute, give it a shot. Okay, so we've got 2 things here. This first one is a nitrogen, and what's this number here? 2. So it's dinitrogen. And let's see, we have a hydrogen and there's 4. So the word for 4 is tetrahydride, because the ending has to be an I. We wouldn't say dinitrogen tetrahydrogen. The second one takes an "ide." It's just one of those rules. Okay, got another one here. It's a little bit cut off, but this time let's see if we can go from words to formula. This is, let me see if I can drag this down a little bit more for you. There we go. That should work. Pentaphosphorus trichloride. Okay, see if you can write the formula from that. If you can't yet, don't worry. That's what class time is for. Homework time is for the notes. Okay, once you've given that a shot, let's see. Pentaphosphorus. So you're going to have P5 and chloride. So that's going to be Cl with what number? 3, because it's trichloride. So P5Cl3. Again, please read the chapter. Again, that's the naming is probably the part that's the most complicated. That's going to be page 227 to 229. You're probably going to want to take a look at that. Try some practice problems from the book. We will work more with these next time. Thanks for listening. Don't forget to do the whisk.